large SGD data set. Thank you. Recording in progress. Great. Some recent research I did using a large SGD data set from the Kona coast of Hawaii. Because this also relates to the overall theme of using big data, novel data analysis techniques, and AI to better understand SGD. In this study, we used a 2-year, 1-hour resolution SGD data set that was deployed.
Can I ask you guys, sorry, just a second. Can I ask everybody to mute their microphones, please? Okay, thank you. Sorry, Trista.
Yeah, no, all good. Right, so in this study, we used a 1-hour resolution SGD data set of 2 years of length. It was deployed in Kiholo Bay on the Kona coast of Hawaii. And we coupled these data with CTD measurements, oceanic and meteorological measurements in an attempt to better quantify relationships between atmospheric, terrestrial, and oceanic forces and their roles in modifying groundwater levels, SGD, and salinity. The subsurface of the Kona coast is poorly characterized. It's quite complex, meaning it can be challenging to model using traditional hydrological models. So the goal here was to provide a template for other methods that can be used to arrive at similar goals to a hydrological model. Our primary objectives here were to constrain the relative contribution of superimposed SGD drivers, establish temporal lag between processes that influence SGD, and evaluate the overall impact of anomalous events on SGD. And I'm just going to cut to a few salient outcomes from this research in the interest of time. One of the analyses we conducted aimed at looking at the relative importance of processes influencing SGD at the Kiholo Bay site. And to do this, we conducted a random forest regression. This is a machine learning algorithm to assess the factors that had the greatest influence. We did this on several temporal scales. Here I show the 1-hour and 3-month average temporal resolutions. The plots show the relative importance of each feature of interest with respect to SGD. And SGD dynamics, as we know, reflect both marine and terrestrial driving forces. However, the importance of these forces depends on the temporal scale that you're evaluating at. So at the 1-hour time resolution, tidally influenced parameters have the greatest influence on SGD, making up over 65% of the relative contribution. In comparison, at the 3-month average temporal resolution, these longer-term seasonal effects, such as precipitation, become the most important. We also used cross-correlation to evaluate the relationships between precipitation, groundwater levels, SGD, and coastal salinity. Here, the top plot shows precipitation in blue, groundwater in red. The middle plot is groundwater, and then that's plotted against SGD in yellow. And then the bottom plot has SGD, again in yellow, and then coastal salinity in teal. And these are all with respect to time. Higher groundwater levels typically preceded higher SGD. However, as SGD is not solely influenced by the groundwater level, the signal response from this graph alone is less obvious. SGD also influences coastal salinity, and these two parameters have a negative relationship with one another. And as we all, I think, understand why, with the exception of major precipitation events where surface runoff and rainfall also influence salinity. And while these relationships are intuitive, I think especially to this group, actually quantifying them can be a challenge. And so I mentioned on the previous slide that it's sometimes difficult to tease apart these complex relationships between variables. And so here we used a cumulative sums or Q-sums analysis to demonstrate quantitatively that higher precipitation leads to an increase in SGD. And so the plot on the bottom shows precipitation in blue and SGD in yellow over time. And then from that, you can see the relationship maybe isn't as clear that precipitation, an increase in precipitation would precede an increase in SGD. So then we did this cumulative sums analysis looking at driver response relationships. And the plot on the right side of the slide shows the results of that. So the underlying data are in those green dots, that's SGD versus precipitation. You can see it kind of looks like a mess, as I think it typically does when you plot these relationships. But through the cumulative sums analysis, and that's shown in the black line, plotted on the secondary y-axis, it actually is showing that precipitation is driving an increase in SGD. And so this is just an example of some of these kind of newer techniques, or maybe less traditional techniques, and how they can be used in the context of SGD research. But I really wanted to focus more today on artificial intelligence. So I'm going to jump now into the main topic today. What is artificial intelligence? In a very general sense, AI is the use of computers and machines to simulate human intelligence. For instance, machine learning is a type of AI where a computer learns patterns through algorithms and data. And then deep learning, which is the type of machine learning I will be focusing on today, is a type of machine learning that is inspired by the structure of the human brain. In deep learning, the computer learns patterns through neural networks that are trained by large data sets. And there are many popular applications for deep learning. For instance, it is used in image and facial recognition, translation. So if you go to Google Translate and just start typing in any language you want, it should be able to predict or tell you what language you're typing in. Medicine, there's been a lot of research about, for instance, cancer detection and automation of imaging for cancer detection, where actually deep learning has been able to not only outperform humans in this task in terms of accuracy, but also in terms of detecting cancers earlier. Targeted experiences such as Netflix, Spotify recommendations, or advertising. And it's also being increasingly used in the natural sciences. So a few examples here where deep learning has been used in oceanography include wave and current modeling, stream flow prediction, and climate modeling. And here's a schematic illustrating the basic structure of a neural network. The basis of deep learning involves the training of a network where you have input variables that are fed into a model, and then they're trained with an activation function. And these activation functions can include linear or sinusoidal functions, for instance. The model then goes through this process many times. Each time it remembers the weights from the previous iterations, and it learns how to minimize the error. This is called the loss function, associated with the observed versus the predicted or modeled data. And I'm actually going to break the rules of PowerPoint and presentations over Zoom. And I'm gonna go to the website that I've added the link at the bottom of the screen, because I think it's a really great demonstration of how this process works. Natasha, am I sharing a browser window now?
Yes, you're good.
Okay, awesome. So this is really fun to play with. I recommend if you like these kind of things. But basically, you set your learning rate here. So we'll just go with the defaults, an activation function, TANH, or that's fine. I'm going to ignore the regularization right now, and then you can have two different types of problems, a classification or regression. And I'm just going to keep it on classification for simplicity. So here are our underlying data in this example problem, the orange and blue, and it's going to try and learn where it should categorize the orange and blue data sets. This refers more to the model complexity, so you can add hidden layers and neurons, so how complex you want your model to be, how many features you want to feed into your model, and then what does your output look like. So I'm just going to press play right here, and voila, it's very quickly is able to isolate that the blue is in the middle and the orange is on the outside. And so this is a very simple model, of course, but it's a great example for how deep learning works. I'm going to do this one more time, and I'm going to hit pause earlier just to give you a little bit of an idea. So this is the loss curve while it's training for the test and training sets. And you can see as the model learns, it reaches a minimum that it's quite happy with. So this tool is a lot of fun. I highly recommend checking it out when you have time. Otherwise, I'm going to go back to the presentation now. And yeah, all right. So one of the first questions we asked when building this project was, what are the variables that will be most critical for prediction? How does one best simplify a complex system? SGD is quite complex, environmental problems are quite complex. So what are the really important factors to take out? The other complicating factor is that deep learning requires large data sets, and so you have to have both enough data and then also messy data sets further complicate the algorithm's ability to model the system. So in the context of SGD, we decided the best approach would be to model or to use the model to predict radon concentrations and using tidally influenced factors and parameters that influence atmospheric evasion. This decision was initially based upon literature and previous knowledge, but then was also later confirmed as optimal through stepwise calculations evaluating model performance. So the data used in this study come from radon time series data sets from around the globe. These are shown on the map, the locations. This includes about 39,000 data points in all. All time series used in the study were at a 1 hour time resolution, and they were of at least 24 hours in duration. Our variables of interest include water depth, water temperature, salinity, air temperature, wind speed, and then radon. And as you can see from the table, as well as the density plot on the top, these data sets represent a wide range of field conditions. Radon data were either measured with a RAD7 or with an autonomous gamma spectrometer called the SGD sniffer. That was what collected the data set I was talking about previously. And then the air temperature and wind speed data, which we used as proxies for atmospheric evasion, were obtained from local weather stations. To construct the deep learning models, first the data underwent some pre-processing, including normalization. All coding was done in Python using Google Colab. If you're unfamiliar with Google Colab, it's a free cloud-based Python coding environment with access to Google's GPU computing power. It works kind of like Google Docs, but instead for Python coding. And it's a great collaborative tool for collaborative coding, teaching, and it's also running great for running resource-intensive programs such as what you need for deep learning, because it's a great alternative to a supercomputer. So the deep learning coding was done using the Python package TensorFlow with Keras API, and all models were set up with an 80-20 train validation split, meaning that 80% of the data were used for training, and then the remaining 20% were used to validate the model accuracy, that the model can accurately predict the data. From here, two different deep neural networks were constructed. First, a fully connected neural network, and then secondly, a 1D convolutional neural network. The two models have different goals, and I'm going to talk a little bit more about them in the following slides, but I'm going to spare you all the details about how these models operate. Although, of course, if you're interested, please feel free to reach out and we can chat more. After the models were run, model performance was assessed by evaluating the loss function, which in this case, I used the mean absolute error, R-square values, and the root mean square error. Additionally, we ran some statistical tests to compare the observed and predicted data. So quickly giving a brief overview of the two models. First, the fully connected neural network model was constructed with the purpose of predicting radon activities. Inputs for this model include water depth, water temperature, salinity, wind speed, and air temperature. And to capture the temporal marine-driven dynamics, depth, water temperature, and salinity at plus or minus 6 hours were also added as inputs to the model. The main utility of this model is primarily to predict radon from inputs that are easily measured from a CTD sensor or a weather station. The 1D convolutional model, on the other hand, uses a technique that's commonly used for time series in deep learning. Here, the model takes water depth, water temperature, salinity, and radon from the previous n time steps, and then uses these, predicts these 4 parameters at a future m time steps. And so for this model, we trained and validated it exclusively on the long-term 1 hour resolution data set from the Kono Coast. and then used a process called transfer learning to test the model with other locations. We defaulted the values for the previous to the previous 6 time steps to predict the future 1 time step in the future. And then this model can primarily be used for gap filling, for instance, if a sensor is working intermittently, or for short-term future predictions. So how do these models perform? We're going to start with the fully connected neural network, which, as a reminder, has water depth, temperature, salinity, air temperature, and wind speed as inputs, and radon as the output. And it was trained and validated with data from diverse field sites globally. Here we can see the models actually really able to nicely predict radon concentrations. And so the plot on the right side of the slide shows the observed versus predicted radon for both the training data are represented by the black dots and the validation represented by the blue X's sets. The corresponding R squares were 0.79 and 0.73 respectively, demonstrating a strong correlation between the observed and model predicted radon. The plot on the bottom side of the slide shows the evolution of the loss function. If you recall in that demonstration I showed earlier, that was that curve that decreased with time. Here again, we use the mean absolute error, and you can see that both the training and validation sets reach a minimum. They did not learn too fast, and that the model is a good fit for the data. I mean, there's no overfitting or underfitting occurring. To further bolster the hypothesis that the fully connected neural network model successfully models the data set, we conducted a Wilcoxon-signed rank test to compare the observed and predicted data for both the training and validation sets. The Wilcoxon-signed rank test is a non-parametric test that compares 2 distributions. Similar to a student's t-test, except that it can be used for data sets that do not have a normal distribution. And at the 95% confidence level, we were unable to prove the null hypothesis that the observed and predicted data were from different data sets. So now I will talk about the second model, the 1D convolutional model. As a reminder, this one was trained and validated with data from Kiholo Bay and uses values of water depth, temperature, salinity, and radon from the previous time steps to predict future time steps, or predict all of these parameters at future time steps. So here I'm showing the results from Kiholo, where we used the previous 6 time steps to predict 1 hour in the future. And as you can see from the plots, the model performs quite nicely. The observed and predicted data had an R squared of 0.97 and 0.92 for the training and validation sets respectively. And the loss curve once again demonstrates the model is a good fit for the data. From there, we then took the model that was trained and validated using the Kiholo data set, and through a process called transfer learning, we tested it on some other locations. I'm just showing a few examples of the model's success here, but in truth, the plots look very similar for all of the sites we tested. The 2 examples here are from Florida and Alabama, and as you can see from the plots, the observed and predicted radon are nicely correlated with one another. And here's just another way of looking at the same results. I always like providing as many visuals as I can because I think it's a good way to conceptualize what's happening or what the results look like. And so these plots, but I think these plots really drive home the success of the model well. So here we have the observed, this is observed radon in the blue, which you can barely see, and then the predicted radon concentration in the orange. And this is all with respect to time. And the main takeaway here is, yeah, it does a great job of predicting the data. So as I mentioned previously, the default time steps for the 1D convolutional model, we're using this the previous 6 hours to predict 1 hour in the future. But we also tested this using other numbers and inputs for inputs and output time steps. And so here we have a plot showing the R square value for several variations of input and outputs for various sites that we tested. And you can see here, the main takeaway is really that the model is still able to successfully predict radon, even if you're predicting, say, 24 hours in the future. So it's a pretty exciting result. So deep learning facilitates a novel analysis of in situ radon data that can then be used to estimate SGD. And theoretically, the fully connected neural network model could be used for long-term SGD prediction from just a CTD sensor and local wind and air temperature measurements. This is provided that that SGD location already has enough data in the model, and assuming that there are no anomalous conditions occurring that were not already accounted for during the training period. But that means then that this method has the potential to be used for long-term SGD prediction. And I think this really unlocks the potential for increasing both temporal and spatial scales of data. And I'm thinking back to the most recent review by Taniguchi et al. In 2019 that posed these kind of 5 big remaining questions in SGD, including addressing spatial and temporal scale, climate change, global estimations, muddy shorelines, and sustainability. And I propose the use of deep learning may be key in driving answers to these questions and more. And that actually really the use of a lot of these big data techniques, as has been found in other fields, can really begin to push the envelope for the research potential within the field of SGD. Of course, there are a few limitations here. Deep learning is a technique that is really driven by data. I mean, it's very much a black box technique, and its modeling capabilities really improve as the number of data increase. So here we've used a relatively small data set in the context of deep learning. Many deep learning models account for millions of data points. More data, particularly from geographically and hydrologically diverse field environments under a range of field conditions, will really help improve the model performance. Additionally, based off model runs that we ran where we had groundwater level data available, and then we could calculate the vertical hydraulic gradient. I think that we would see then significant model improvement through increased monitoring for these kind of data, because if that could also be used as an input to the model, I think we would see a substantial improvement. Despite these limitations, though, the model performs very nicely, especially considering the relatively large uncertainties associated with radon measurements. And with that, I'd like to offer the following take-home messages. The research I presented today demonstrates the utility of using big data techniques and artificial intelligence in SGD research. Deep learning successfully models radon concentrations. It can be used as a gap filling method and can predict future radon concentrations in both the short and long term. One of the advantages of using radon, or using this method to calculate radon, is then you can also calculate SGD using your favorite end member or parameters you want to put into your SGD calculation. I think there's strong potential to use these methods to further investigate major outstanding questions in SGD research. And as the field of SGD now has sufficient data and maturity, to use these more data intensive methods such as deep learning, I think we're in a really exciting place for the future of SGD research. And yeah, I want to thank you all for your attention. Again, to Natasha for inviting me to speak today and organizing the seminar. I want to acknowledge Peter Sadowski, Madi Bakad, and Christina Richardson for their help with various aspects of this research. Funding from this research when I was based in Hawaii came from the Hawai'i EPSCoR program, the EKY project. And yeah, I think we can really start to open a discussion here about the potential for these methods and what gaps can be used or what gaps can be filled by using them. And yeah, thank you.
Thank you, Trista. This is very, very exciting. And with that, I'm gonna turn it to the audience. And yeah, guys, what do you think? Just unmute and directly ask questions. Anybody?
Hi, this is Dorina from Texas A&M Corpus Christi. I have a question, and maybe I didn't pay close attention. Do you think your model applies to any environment where, I mean, I'm thinking about the salinity component that you used in your analysis. And in where we work here, it's a semi-arid region, and we rarely see significant changes in salinity that can, help us understand hydrologic processes. Most of the time is we have reverse estuaries, and pore water is extremely saline, or the groundwater is also saline. So would it be applicable to an environment like this?
Right. Yeah. Thank you for your question. My perspective on this, and I love going in the field and taking radon time series measurements and et cetera. So I'm not suggesting this is the replacement for it. I would be inclined to take the radon measurements for some amount of time and put it into the model before I would feel comfortable doing that. So I see this as more of a means to upscale, both like in terms of time and then maybe also spatially. I think once the model has seen a site, it can very nicely work with it. But I think, especially as you're saying, there's such a large range in field conditions. I mean, maybe it would work beautifully. We do have a really interesting range, like some really cool arid sites in there. So maybe it would work well. But yeah, my recommendation for this at this point is to add it to the model if that's something you want to do, and then you can expand from there really easily.
Thank you.
Yeah, just to add to this question, Trista used a data set from Alaska, from Kasutsina Bay, that we collected a few years ago with Adina. And in this side, I collected the data. I remember that the salinity didn't change more than 1 or 1.5 ppt. So perhaps even at this stage, Trista's model maybe could take care of those kind of cases.
Yeah, actually, and also Bill Burnett provided a lot of very strange radon time series data sets that are in the model as well, that also have some very little salinity change, but still seem to perform quite well.
Mm-hmm. Any other questions?
I think Bayani has his hand up.
Okay.
Yeah.
Just go and
thanks.
ask. Yeah.
Thanks, Trista. That was super impressive. So my question is, you were trying to predict radon, right? But most people measure radon to predict SGD, to predict the discharge. I wonder if you've tried to do the opposite, right? And then of course, head gradients directly are linearly related to discharge. So I'm wondering whether you've tried that, because ultimately it's SGD we want to predict, and radon is a step towards that.
Yeah, thank you for your question. Yes, I did try to do this. And the issue I ran into was there is not enough. The model really wanted to have the hydraulic gradient, the vertical hydraulic gradient, as an input to predict SGD. And there are not sufficient number of sites that have SGD time series with that parameter available.
Cool. Thank you. Awesome job.
Thank you.
If you guys have questions, again, yeah, go ahead.
Bocha?
Hi, Trista. Hi, Natasha.
Hey, Bachao, how's it going?
Good. Trista, nice work. I have a couple of questions. The first is, are you predicting only the radon concentration in surface water, or can you do, many depth resolutions?
Currently only in surface water.
what's the depth?
So the depth of the surface water varies, right? We have a range of field sites where the ocean water level is quite highly variable. And I go back to this Alaska data set that Natasha just brought up, which I think the maximum depth there was 16 meters at high tide. But my assumption, though, in all of these data sets is that it's really the surface layer that's being measured, right? Because when we conduct radon time series, we're really interested in that top layer. So I would suspect that if you're trying to monitor radon concentrations at a bottom depth, it may not work as well. Maybe I'm wrong, but it's not what's been input into the model.
Yeah, I'm just curious. What's the scale are we talking about? If it only works on the very surface water, like 1 or 2 meters, probably we are looking at a very near shore scale, very near shore area, and the average of the whole water depth maybe can give you very different answers. If you are talking about, we are looking at a different water depth, right?
For sure, yeah. So I assume that these are near shore measurements. This is a near shore radon prediction for sure.
The second question is, are we talking about the total radon concentration or excess?
Radon in water.
Total. I mean, is both excess plus the supported by radium-226, right?
Correct. Yeah.
So do you think radium-226 is important to the results?
That's a great question. It's one that I was unable to account for given the data sets. I would say given the model's success, it's probably not a critical factor, but is certainly one worth investigating further.
But is it currently is not involved in the model now, right?
Correct.
I mean, radium-226 is not involved in the model yet.
Correct. It is not. No.
Okay. We are collecting radium-226 data globally on the coast ocean, and hope we can talk about more about the data and the questions.
For
Great
sure.
work.
For sure.
Thanks.
Thank you.
Thanks, Patel.
Thanks, Natasha.
Hi, Trista. This is Will Wolf here. We're with Dr. Mergel at Texas A&M University Corpus.
Hey.
You got me? Hey, this is really fascinating stuff, and it's great to see someone doing something similar to our work. We actually have a little overlap here. I'm going to go back to what Dr. Cardenas Bayani said about modeling rather radon itself, in surface water as opposed to your final output, your SGD or inventory or anything like that. So you said you attempted, or you ran the model as just radon, but you also ran it with other as inventory. Did you find that it was more effective? Like it was a more powerful model just to model radon itself in surface water rather than some iteration of that, something, because there's a lot of other factors that go into it once you have radon in surface water. But that was the strongest result, so you went with that?
Yes, that's correct.
I'm sorry, I missed a portion of your presentation, but it's really fascinating stuff. We'll have to follow up because it's really great to see this, especially random forest getting used in this way.
Thank you. Thank you. Yes, please reach out.
Yeah, we should. I'll give you an email or something.
Trista, there is a question by Chris Smith. Do you want to read it from the chat?
In the chat. Okay.
Yeah.
So along those same lines with respect to radon versus SGD prediction, do you think you could develop efficient models for individual sites that make the linkage between radon and SGD? Or is it too data limited to develop efficient models? Yeah, actually, so the reason that I haven't, well, I mean, I've done this, but I didn't speak about it, is because I feel that, and maybe I should just do this again. But basically because radon is such a strong predictor of SGD, it just felt like I was predicting, like I was using the model input. It felt too close to the model output, I guess. But now that I'm thinking about it, and now that you've brought this up, I've realized that it was actually a really strong result when I did that, and that would be a very simple thing to do that would have a great result. So thank you for that. Sometimes you get very lost in these projects and you forget to do some of the obvious things.
Thank you. More questions?
So I do have a follow-up question, Trista,
Okay.
if nobody else is asking a question. I'm more curious about the AI techniques you're using.
Mhm.
So you said, of course, they were developed for massive data sets, right? To get insight from massive data sets running through a black box. In your experience, in your background now, I wonder, does it make sense to use AI and the techniques you used for sparse data sets or low dimensional data sets, or maybe even low dimensional data sets, meaning different kinds of data, but there's only 15 of each, versus, you know, I've got 3 kinds of data, but I've got 3,000 of each.
Right. Specifically with deep learning, I would say at a bare minimum, you'd want 1,000 data points, and that's really a low, like the very, very low end. And at that point, you would, hopefully the data are not messy. So that this is one of the challenges, I think, with deep learning, is that you need a just absurd amount of data. And even the amount of data that I put in, which is, you know, what, 39,000 data points, is considered small. So it's one of those trade-offs. I mean, you can always try it, and if it looks beautiful, then maybe you just have the right data set that has a very easily predictable outcome.
Thank you.
Thank you.
Thank you. Okay. Any more questions?
Hi, Trista. This is Xiaoyi from Ocean University of China. And nice talk, great presentation. I have a quick question. So in your first slide, you show that there are several factors influence the SGD. And I found it interesting that wind direction is more important than wind speed in controlling the SGD. I'm just curious, any ideas about that? Why wind direction is more important than wind speed? Thank you.
Yeah, thank you for your question. So direction versus speed. I think in the context of this problem, when you're trying to generalize over many diverse sites, it's really hard to even begin to address the speed question, because I'm just thinking of groundwater residence times, surface water residence times. It's so highly variable. So at that point, the directionality, how these processes influence one another, I think became the more critical input.
Okay, thank you.
Hi, Krista. This is Bo Zhang from University of Alabama. May I ask one question about data?
Of course.
Go.
So when you do analysis, and I'm pretty sure you applied your model to different sites. So some sites we may have a high confidence, high accuracy about the prediction. Some sites maybe we have fair accuracy about the prediction. Do you know what is the reason or what is the procedures to ensure that your model will produce a high accuracy for a certain site?
Okay, so I'm trying to make sure I understand the question. As it is now, or sorry, yeah, Go ahead.
So for example, you apply your model to set A, you get accuracy of like maybe 90%. And then you apply your model to set B, you get another accuracy maybe 85. So my question is, did you dig why set A has higher accuracy and where set B has lower accuracy?
Yeah, for sure. So I should specify first that this question would only be relevant to the 1D convolutional model because the other model was not differentiated by site. But for the 1D convolutional model, it seemed to really be driven by the amount of data, so the length of the time series. So even for sites that had a really wide spread of conditions, if there were more data available for that site, it seemed to perform much better.
Bo, did we lose you?
Yeah.
What do you think?
So what I mean, did you, for example, if you have for other set A, if you have higher accuracy, so for your model, is the set A has more like thermal features with your state, thermal features with the site you use for training or just other reasons? You see what I'm talking about. So for example, when you do a training, you're using the data come of certain site. If that certain site has thermal features with the set A, should we get a high accuracy? Or if your the features at the training site has a different features with set B, then we will get a lower accuracy. You see what I'm talking about?
Yes, no, so that's correct. I think one of the beautiful things about the Kiholo data set is its length and the fact that that data set represents, even though it was, exclusively representative of, Kona coast of Hawaii, represents a wide range of conditions. So, multiple tropical storms came through, there was a tsunami, all sorts of really kind of fun stuff, events occurring in that data set, which I think have helped the model learn a pretty diverse set of conditions.
Okay, yeah. So and my second question is about so when you build a model, so I think you have several inputs. So which one is the most important to predict the random in your model?
Which variable is the most important? I would say the water level, the water depth would be the most key, but in honesty, I would say that the water, if I had to pick three, right, it's going to be the water depth, salinity, and water temperature. But the model significantly improves when you add in air temperature and wind speed.
Okay, air temperature.
Which was one of the parameters that, remember when we started talking about that, is what air temperature has something to do with HGD. It's such a parameter that is, we don't think about this parameter when we think about HGD in general. And there you go, you have this very good correlation between air temperature and HGD.
Okay, thank you so much. Fantastic work.
Thank you.
Thank you, Bo. Bo had helped a little bit with developing this model as well. And mostly, in conversations with him, we start thinking about different ways to improve this model. Yeah, I was a little bit surprised. I think you said at the beginning of your presentation that anomalous conditions that the model doesn't know are probably, you don't want to have data set that has been impacted by some anomalous conditions.
Or, you do, right?
But yeah, you actually want to have those to train it better.
Right, exactly. And so, yeah, the challenge with deep learning is that it only can understand the data that it's seen, right? And so if you start feeding it something that it's never seen, conditions it doesn't understand, it's not going to know what to do with it. And so anomalous events are fantastic for training the model. And my hopes with this model is that this is a baseline that then can be updated with time as more data are collected, and so that then its prediction power can become, quite powerful.
Okay, great. So the question is then, once you publish this work, do you think the model could be somewhere published in, have free access for other people? Is that the goal?
Yes, that's the goal. And hopefully it can keep evolving and people will want to contribute to it.
Great. Do we guys have more questions, or we should wrap it up? I don't see any other raised hands. And with that, I'm just gonna say again, thank you to Trista, awesome work. We are looking forward to see her publications and the model, so each of us can try it, reach out to her, and great talk, Trista. Thank you.
Thank you.
Bye,
Thanks,
everybody.